Okay, let's get started. Good morning, everyone. Today we'll look at the week two questions from the previous year. Just give me 1 minute. Share my screen as well. Can you people hear me fine?
Yes, sir.
Okay, yeah. Can you people see the screen as well?
Yes, sir.
Okay, okay. So, good morning, everyone. Today we'll discuss previous year's week two questions from the course Drug Delivery Principles in Engineering. Okay, so getting into it, the first question reads for a given polymer, rank the glass transition temperature, melting point, and the crystallization point from the lowest to the highest. So, which comes first for any given polymer? Is it the glass transition temperature, the melting point, or the crystallization point? Any idea? So let's go
Second
through.
option, sir.
Yeah. So TG, and TM, is it? Okay. So let's go through the options one by one. TG, TM, and TC in the order of lowest to highest. TG, TC, TM, TM, TG, TC, TM, TC, TG, or TC and TM only, and the glass transition temperature does not exist for a polymer. TG and TC, but the melting point does not exist for a polymer. And I guess this is also the same option, but TCTM, TG, and TCTGTM. Okay, so let's briefly go through what the glass transition temperature, the melting point temperature, and the crystallization temperature are for polymers. The melt transition temperature, or TM, is the temperature at which all the crystalline regions melt and the crystallinity disappears in a polymer. And the glass transition temperature is the temperature at which the hard and brittle amorphous material becomes viscous and rubbery in a reversible way. And obviously, the crystallization temperature is the temperature at which the material transitions from being this amorphous liquid back into a crystalline state, right? So that's what the TM, TG, and TC are for a polymer. And how do you measure this TM, TG, and TC? Any idea? So how do you measure this Tg, Tc, and Tm of any substance? Need not be polymer. So let's say for a given substance, you want to measure some particular temperature at which the properties of the material changes. Or let's take a simple example. Let's take a cup of water. You want to know at what temperature it boils, right? So how do you measure that? There's a very specific instrument to sort of slowly increase temperature. So slowly feed in more and more energy into the system, and at the same time detect the amount of heat flow that's happening or the conductivity that's happening. Does anyone know what this instrument is called?
So thermometer.
Thermometer, sure. So the problem with thermometer is it does not increase the temperature by itself, right? So you can detect the change in temperature, but you cannot gradually increase the temperature and measure the conductivity of the material. So to do this, there is a very particular instrument that does this. Have you people heard about calorimeter?
Yes, sir.
Yeah, so calorimeter is what people use to measure the change in conductivity with an increase in change in temperature, and we can use the calorimeter. So there's something called DSC. We can use calorimeters to measure this TGTC and TM. And if you guys remember, so this is what typical graph for a polymer or most of the polymers looks like, where as you constantly keep increasing the temperature, first we hit the glass transition temperature, where if the polymer is crystalline, the crystallinity starts to disappear, right? So as you keep on increasing the temperature, the crystallinity starts to disappear, and the polymer sort of becomes amorphous to an extent of time. And if you keep increasing this temperature, you'll reach a point where you're supplying the system with enough energy that the crystallinity reappears. So the polymer becomes crystalline again, and there is this reduced heat flow. But if you keep on increasing this temperature, there is this point where it's called the melt transition temperature, where it sort of completely goes away, right? So the crystallinity completely disappears because there is so much energy that's being supplied to the system. All the ordered bonds are broken. So that's what the melt transition temperature is. So going back to the question, what comes first is the glass transition temperature, where if there is any amorphousness in the polymer, it sort of becomes viscous and rubbery, and crystalline temperature, it solidifies and becomes not solidifies, it becomes ordered and becomes crystalline, and eventually the melting point where all of this crystallinity disappears. Okay. Moving on, which of the following statements is not a limitation of a polymer drug conjugate? Choose two statements. Biomolecules or drugs can lose activity during conjugation process. Purification of unreacted polymer biomolecules and any reaction products is necessary before in vivo application. Sterilization process now involves polymer stability, can be viewed by regulatory authorities as a new drug entity. Polymer drug conjugates can improve bioavailability of many poorly soluble drugs. If non-compatible, they can trigger inflammatory reactions, and polymer drug conjugates can be made targeted for specific applications. So they're asking which of the following statements is not a limitation of polymer drug conjugates. Any idea? So can biomolecules lose their activity during conjugation process when you're making a polymer drug conjugation? So let's say I have some polymer PLGA, and I have a biomolecule or a therapeutic agent that I want to give to the person. So mRNA. So I want to conjugate this mRNA to the PLGA. Will it lose activity during the conjugation process? So yes, the biomolecules or the drugs can lose activity during conjugation process. So oftentimes these conjugation processes require the use of different temperatures or different solvents or so on and so forth. So they have an effect on the biomolecule, especially if the biomolecule is something that's very labile, like mRNA, or where the structure is very important, like proteins. Like you can't just simply conjugate proteins, right? So you need to add linker sequences and so on and so forth. So they can lose their activity during the conjugation process. So the next point is purification of unreacted polymer biomolecules, and any reaction products is necessary before in vivo application. Is this true? So in vivo application is wherein you're basically injecting it into the body, right? So do we need to purify our products before we inject them into the body? What would happen if you do not purify? Hello, you guys can still hear me, right? Hello. Um, Not sure if you guys can still hear me.
Yes, sir.
You guys can hear me? Okay, great. Uh, okay, okay. Yeah. So what would happen if you do not purify? So you want to purify because you do not first of all want to inject foreign materials that are unnecessary for your process, right? So there could be endotoxins, there could be so many other things. So uh, that might cause severe immune reactions. So you would definitely want to purify whatever you're injecting into the body. And in fact, there are very strict protocols to ensure that purification happens before anything goes into the body. Yeah. So the next point reads sterilization process now involves polymer stability. Okay. So do we need to take consider polymer stability into our process of sterilization? So, what are the usual processes of sterilization? So, you want to sterilize something, what would you do?
Autoclave.
Yeah, autoclave. So will autoclaving affect polymer stability? So, what is autoclaving? So, basically, you're subjecting the substance to a very high pressure, 15 to 20 kilopascals of pressure, and you also subject it to a very high temperature, right? 121 degrees centigrade. So does this process affect polymer stability? Yeah, so we've just talked about this. So obviously increasing temperature would change the nature of the polymer, right? So 121 degrees centigrade for a given polymer might just be the melting temperature. So you're melting the polymer at that point, or crystalline temperature, you're crystallizing the polymer. So temperature plays a very big role in polymer stability. So obviously you cannot then start using autoclaving for all of your polymer uh, formulations, right? So you need to take that into consideration. So maybe gamma, you need to do something like gamma irradiation to sterilize the polymer. So sterilization process involves understanding polymer stability and taking actions according to it. I think, yeah. Yeah, so the next point is can be viewed by regulatory authorities as new drug entity. So, is that true? So let's say I have a polymer, PLGA polymer. I won't make any new drug. I'll just take something that's regularly available in the pharmacy, something like PLGA, aspirin. Or paracetamol. So I'll take paracetamol, I'll load it into the PLGA particle. Will that be considered as a new drug entity by the authorities? Or is it just paracetamol? It has already been tested and uh, clinically viewed, right? What do you guys think? So if I take a polymer and I conjugate it with paracetamol, a routinely used, well-studied, clinically approved drug with very good track record of side effects and short-term and long-term side effects. I conjugate it to my polymer. Will the regulatory authorities think it's a new drug or it's just paracetamol that has previously existed?
No, sir. They will think that that's a new drug, I think.
Yeah, so that's a major regulatory hurdle because even though it's just paracetamol, you're also introducing a new system, right? So you're introducing a polymer that has not been very well studied or does not have as much of a track record as paracetamol itself, and you do not know how these two interact with each other, and if they have a combined interaction with the body, so it will be considered a new drug entity. So that's a drawback. Okay, the next option is polymer drug conjugates can improve bioavailability of many poorly soluble drugs. Is this true? Can polymer drug conjugates improve the bioavailability of a poorly soluble drug? So they can. There are several examples in the market as well. So what happens if a drug is poorly soluble? Uh, why does it not have a very high bioavailability? So it's not going to dissolve in your blood and get distributed in your body, right? Or dissolve in your extraluminal space and get distributed in that particular organ. So that's why it does not have a very good bioavailability. But if you can somehow circumvent this or improve this, so what you can do is you can take this drug that has very poor solubility and you can conjugate with your polymer and you can give that polymer. So what happens is it doesn't matter if the drug is soluble or not, it's going to stay there. In case of just the drug alone, there might be very rapid elimination of the drug when it's not very soluble. So that's one of the major issues. So polymer drug conjugates can improve the bioavailability of many poorly soluble drugs. That's correct. So obviously this is not a limitation, right? So in fact, this is an advantage. So that would be one correct option. And the next option reads, if non-compatible, they can trigger inflammatory reactions. Is this true? Can polymers trigger inflammatory reactions? So maybe you haven't gotten to that point of the course yet, but yeah, so they do trigger inflammatory reactions if they're non-compatible. In fact, they can trigger the immune system as well and develop antibodies. Your immune system can develop antibodies towards components of these polymers. So that's a limitation as well. So that's something that you need to consider. And moving on, so polymer drug conjugates can be made targeted for specific applications. Is this true? Can you tailor make polymer drug conjugates for extremely specific applications? So I'll give you an example. So there is this drug called baclofen. Uh, I want to deliver it specifically to the brain, but if I give the drug intravenously, it's going to get distributed in the spinal cord or throughout the rest of the body. Can I make a polymer drug conjugate to target this specifically to the brain? Might be a little challenging to cross the blood-brain barrier. Maybe a bad example, but let's say if I want to target to any other organ, let's say uh, I specifically want to target this drug to the lungs. Can I do that? So the answer is yes, mostly because you have you have a polymer that has a very large surface area, right? So you can add several targeting or homing peptide sequences, targeting proteins, so on and so forth to sort of redirect your polymer. Just because of the fact that it has such a large surface area, you can do a lot of modifications to it to prevent it from accessing certain sites to make sure that it goes into certain sites and so on and so forth. So that's obviously not a limitation, and that's also an advantage. So if we were to look at the question, which of the following statements is not a limitation? So the advantages would be polymer drug conjugates can improve bioavailability of many poorly soluble drugs, and polymer drug conjugates can be made targeted for specific applications. So they are not the limitations. Is that clear?
Yes, sir.
Uh, moving on. So the next question reads, a gold surface was grafted with a polymer. The ends of this polymer are tagged with four pendant groups, namely groups A, B, C, and D. The pendant groups are weak acids. The modified isoelectric point of the entire polymer was calculated to be as follows. The isoelectric point of A is 4.5, B is 5.5, C is 7.4, and D is 9. These particles are loaded with a positively charged drug on the surface using electrostatic interactions in PBS at a pH of 7.4. Which of the following will have minimum loading? A, B, C, D. What do you guys think? So they have gold surface grafted with a polymer, and the ends of this polymer are tagged with this either A, B, C, or D. And the isoelectric points of ABCD are given as 4.5, 5.5, 7.4, and 9 respectively. Now they want to load a drug onto the onto the gold surface, and they're doing this by this is a positively charged drug, and they're loading it by using electrostatic interactions in PBS, which has a pH of 7.4. Now they're asking which of these four groups will have minimum loading, either A, B, C, or D. Any idea? What is the isoelectric point? Make sure if people are getting admitted. Yeah. Okay. Yeah. So what is the isoelectric point of a chemical?
Sir, when both the positive and the negative charges become neutral.
Right. So an isoelectric point is simply where a chemical will have no net charge, right? So it's neutral. Uh, so what happens at isoelectric point lower at a pH lower than the isoelectric point? So when pH is less than Pi, what happens? Okay. So So yeah, the isoelectric point is a pH at which the particular molecule carries no net electrical charge. So I'll give a simple example. So in this case, we are looking at amino acids. So at isoelectric point, amino acids can exist as Witter ions, where the net charge is zero. So there is equal amounts of minus and plus charges. So the net charge is zero. But what happens at lower pHs, which is pHs less than the isoelectric point, is so basically the negative charges are compensated for. So there are a lot of H plus ions in an acidic environment, right? So this O minus becomes OH simply because of the fact that there are a lot of this H plus ions because it's an acidic pH. But the positive charge is not compensated for. So the molecule becomes positively charged. But similarly, at pHs greater than the isoelectric point, there are a lot of OH minus ions in the media. And what happens is the negative charge or the positive charge gets compensated for, but the negative charge remains. So this O minus remains as it is, but this NH2, NH3 plus gets deprotonated. So the hydrogen goes away, and as a result of this, the molecule becomes negatively charged. So uh, this is Pi, isoelectric point, where the molecule is neutral in charge. If the pH is less than Pi, the molecule is positively charged. But if the pH is greater than Pi, the molecule is negatively charged. So going back to the question, Group A has a pI of 4.5. So if the pH is less than 4.5, Group A will be positively charged. And if the pH is greater than Pi, Group A will be negatively charged. So in this case, they are using a pH of 7.4. 7.4 is greater than 4.5. So A will be negatively charged. And if it's negatively charged, the electrostatic interaction with the positively charged drug is going to be very high. So the loading will be good. So it will attract more of the drug because the drug is positively charged. A is becoming negatively charged because the pH is greater than Pi. So the drug will get attracted and there will be a lot of binding and loading. Same case with B, where 7.4 is greater than 5.5. C is basically going to be neutrally charged. Sorry. So compared to A, B has less of electrostatic interaction with the drug. So we would expect a little bit less of loading. And compared to B, C does not have any charge as such because its pA is equal to the pH that's being used. So it's neutrally charged. It will have very weak electrostatic interactions, mostly stochastic electrostatic interactions. So the drug loading would be very minimum. But if you look at D on the other hand, this has a pI of 9. So the isoelectric point of D is 9. The pH they've used is 7.4, which is much less than 9. So D would be, what charge would D have? Will it be positive or negatively charged? So let's say this is D. This is pH, the isoelectric point is 9 and they've used 7.4. D will be positively charged, right? So D will be positively charged, and we are also using a positively charged drug. So the electrostatic interaction is basically repelling in this case. So D will repel the drug and it will have the least amount of loading compared to all four groups. Yeah, so any questions or is that clear? Is it clear?
Yes, sir.
Okay. Okay, so the next question is which one of the following polymers degrade hydrolytically by near zero order kinetics? Uh, they've given a bunch of options: polylactates, polyesters, polyanhydrates, polyamino acids, polycarbonates, and polyamides. And they're asking which of the following polymers degrade hydrolytically. So, what water cleavage? By near zero order kinetics. So, very efficient and very fast cleavage by water. What do you guys think? Okay, so let's go through these options one by one. So the first option is polylactates. So they have a lactate bond, and although lactate bonds are formed by uh, dehydration, dehydration chemistry, so you'll remove water molecule to condense two different chemicals and form a lactate bond. And they can be cleaved by water, so they're hydrolytically cleavable. But the process is quite slow because the bonds are quite strong. When it comes to polyesters, so they have an ester linkage between them. Water cleavage, they're fairly stable. Water cleavage does not usually happen, and uh, you would require specific enzymes to cleave these ester bonds, right? So, what are these enzymes called? Does anyone have an idea? They're present all over in your body and they're very ubiquitous in nature, so they're present everywhere. They're called esterases. So, specific class of enzymes, esterases. So, they readily cleave this bond, but water need not necessarily readily cleave the polyester bond. Polyanhydrates, on the other hand, they have an anhydrate bond and they're super fast to be cleaved by water. So, they're readily cleaved by water whenever they're exposed to water. Polyamino acids, obviously not, because we know proteins are very stable in water. Polycarbonates, no, and polyamides as well. They require very strong alkaline and acidic conditions in addition to water to be hydrolytically cleaved by water. So they require very low or very high pHs to be cleaved by water. So of all these polymers, only one polymer can get very readily cleaved by water and shows a near zero order kinetics. So that's polyanhydrates. Yeah, so this is the structure of polyanhydrates, a very unstable or very low energy bond to be that's able to be broken by water molecule. Okay, so which of the following are correct with respect to PLGA particles? So they're saying two options are correct here. It is a non-biodegradable polymer. It can be used as a vehicle in gene therapy. They can be degraded at gastric pH. They have not been clinically used. It is not a copolymer. They can be extracted from chitosan-based proteins. What do you guys think? Okay, so is PLGA copolymer? Is it biodegradable? Let me see if we can pull this up. PLG. Yeah, it doesn't have the structure. So is PLGA non-biodegradable or biodegradable? So PLGA is readily hydrolyzable into lactic acid and glycolic acid. And so it's ultimately metabolized by CO2 and H2O in the body. So would you consider that as biodegradable or non-biodegradable?
So biodegradable, sir.
Correct. So PLGA is biodegradable. So this is not true. Can it be used as a vehicle in gene therapy? Therapy? Why not? Right? So as long as you can find an efficient way to load your mRNA into or DNA into PLGA, it can definitely be used as a vehicle in gene therapy. Can it degrade at gastric pH? It can. So at gastric pH,
Yes, sir.
PLGA is very degradable. Has it uh, not been clinically used? So if I go back to this, so it says FDA approved as bioabsorbable sutures. So has it been clinically used? So the sutures that you get when you go to the doctor. So previously, it used to be the case that if you get these sutures, you'll have to go back to the hospital again to get them cut and removed. Whenever you have a cut, the doctor will stitch you up, and after 1 month, 2 months, you have to go back and cut and get this removed, right? But now you don't have to do that anymore. So these sutures will automatically dissolve into your body. So that's because they're made of PLGA, and it has been clinically approved. So it has been routinely used in the clinics as well. So they have been used in clinics. And is it not a copolymer? Let me pull up the structure of PLGA.
It is polymer, sir.
Correct. So it is a copolymer, right? So lactic acid and galactic acid. So it's formed by essentially dehydrating and combining these two structures. So it is a copolymer of both of them. And can they be extracted from chitosan-based products? No, not really, right? Because chitosan is naturally derived and so on and so forth. So yeah, so it can be used as a vehicle in gene therapy, and they can degrade at gastric pH. So those are correct with respect to PLGA particles. Okay. So the next question is, what are the advantages of using polyethylene glycol in drug delivery application? Two options are correct here. So PEG, what are the advantages? Does it have very well developed conjugation chemistries? Is it non-toxic, immunogenic, and can be produced under GMP, good manufacturing processes or practice? Is it highly hydrophobic? And biocompatible, can it easily be phagocytosed by the immune cells? Can it deliver cargo intracellularly very efficiently? What do you guys think? So can PEG deliver cargo intracellularly very efficiently? No, right? No reason for it to deliver any cargo intracellularly. Uh, so let me jog your memories. Oh, sorry. So this thing that you see here is PEG, right? So these squiggly lines. So that's PEG. There's the structure of PEG. Yeah. Yeah. So this is PEG. It's basically used to decorate your polymer for several reasons to either uh, well to prevent access to the polymer, to make it more immune compliant, and so on and so forth. uh, is it hydrophobic or hydrophilic? So if you look at the structure, it has hydroxyl groups at the end.
Hydro.
Correct. So it's extremely hydrophilic. So it will increase, in fact, it will increase the solubility of whatever you conjugate it to, right? So it's not hydrophobic. So the highly hydrophobic, and it's biocompatible, but it's not highly hydrophobic. It's highly hydrophilic. So that would be wrong. And there is no reason for it to deliver cargo intracellularly, right? So like I've shown you the structure, it's not going to interact with any of the receptors. It's just a chemical polymeric structure. So why would it deliver it intracellularly? So definitely no. Can be easily phagocytosed by the immune cells. Again, so it's not a very bulk structure for the immune cells to be able to phagocytose it, right? So uh, first of all, it's not in micron range for the immune cells to phagocytose this drug. And also, in fact, it will prevent immune cells from interacting and phagocytosing your polymer itself. So they cannot be easily phagocytosed by the immune cells. So this is wrong. So all these three are wrong. So is it non-toxic? Yes, it is non-toxic. It's non-immunogenic. Well, there are reports of immunogenicity of PEG, but for the most part, it's non-immunogenic. And it can be produced under good manufacturing practice because it has been widely studied, widely developed across the world, and a lot of people can produce it. And it has been being produced for a long time, right? So it can follow this good manufacturing practice, basically sterilization, ensuring sterilization, and so on and so forth. And so that's correct. And does it have well developed conjugation chemistries? Yes, we know the structure very well. We have worked with it for a very long time. We know what happens when we want to, so we know how to add stuff to it, how to conjugate it to things, so on and so forth. So it has very well developed conjugation chemistries, and it's non-toxic, non-immunogenic, and can be produced under GMP. Okay.
Sir,
Yeah.
sir, for this question, uh, I have marked two answers, but one answer only, sir, correct. but I got only 0 marks, sir. If there is any,
I did not get you. So same question, is it?
yes, sir, this same question, but I have, uh, but I tick the answer as a non-toxic, immunogenic, and can be produced under a good manufacturing practice. But
Mm-hmm.
another option, what I ticked was highly hydrophobic and biocompatible.
Okay.
But they have asked the two options correct, but one option only is correct. But I got 0 marks. Is there is any option for getting half a mark for this question for me?
You can raise the question in the forum. So previously we used to give I think half mark for correct answer, but if you put an incorrect option, so if you put an incorrect option, it will be marked as wrong. If you just tick one correct option, that's fine. You'll get half the marks. But since you marked an incorrect option, I'm not sure if we can do that. But
Okay, sir.
you can talk about this in the forum, so you can ask someone to address this.
Okay, sir.
Okay. Okay, so the next question is, if a particle takes time t to diffuse L millimeters, how long will it take to diffuse 4 L millimeters? Does it take 2 times, 4 times, 8 times, 16 times, 32 times, 64 times, 128 times, or 20 times? What do you guys think? So particle is diffusing L millimeters in time t. How long will it take to diffuse 4 L millimeters? Any guesses? So let me rephrase this question. Let me ask a much simpler question. So let's say a train is moving at a constant velocity. It goes 4 kilometers in 1 hour. How long will it take to go 8 kilometers? So if it's going 4 kilometers in 1 hour, how long will it take to cover 8 kilometers?
2 hours, sir.
2 hours. Correct. So I told you the train is moving at a constant velocity in a direction, right? So is diffusion the same thing as movement or velocity? No, right? So we know the laws of motion are being governed by the Newton's laws. But what would govern diffusion? Fixed laws. So there is something called fixed laws. And diffusion is not as straightforward as motion itself. So the time it takes for diffusion to occur, T is directly proportional to the square of the distance. So if the distance is increasing by 2 times, the particle or whatever is diffusing will take 4 times the time. So even for small amounts of distance increase, the time it takes for diffusion to happen increases drastically. Why? Why is this the case? Why does diffusion happen? So let me ask you this: what is diffusion? So diffusion is the movement of a particle from an area of high concentration to an area of low concentration, right?
Yes, sir.
Yeah. So that's diffusion. Why does it happen? Uh, so why does it happen is much more of a complicated question, but so all of these particles and everything else in nature has some amount of energy associated with it. And because of this, and because of the size of the particles, because they're so small, there's something called Brownian motion that happens. So where they randomly start moving across the three dimensions, right? So when this happens, uh, so if there are a lot of particles, the particles are colliding with each other, and the net displacement is more or less going to be zero if one particle is surrounded by so many different particles. So because it collides with this particle, comes back, collides with this particle, comes back, it's more or less stays in the same place. But so consider these particles to be in a sphere. At the edge of the sphere, what's happening is whatever particle is at the edge of the sphere, it's only colliding with the other particles in one direction, which is pushing it out. So the particle is slowly starting to get pushed out, right? So it will the sphere would sort of slowly start to spread. So that's diffusion. And since there is no predetermined force that's pushing these particles in one direction. It's a random process of Brownian motion. So there is no predetermined force that's pushing them in one direction. So that's why even for small changes of length, the time it takes for these particles to diffuse out becomes much more larger. So this is given by Fick's law. Fick's law sort of states that uh, basically the time it takes for diffusion to happen is directly proportional to the square of the length. So if a particle takes t time to diffuse L millimeters, if you increase this L millimeters by 4L millimeters, so what would happen? So 4L squared or 16L squared, right? So it will take 16 times the time to diffuse uh, 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 so the particle would take 16 times the time to diffuse to this distance of 4L millimeters. Is that clear?
Yes, sir.
Okay. Okay, so the next question is consider that a drug A is loaded into two separate reservoirs whose drug releasing areas are in the ratio of 2 is to 1 and loading concentration of the drugs are in the ratio of 1 is to 2. What is the ratio of mass of drug released in the same amount of time for these two reservoirs? Assume that the reservoirs are flat and non-erodible. The drug diffuses through a semi-permeable membrane in both the cases. Does anyone know how to solve this? So they're loading the same drug into two separate reservoirs, and the area of drug release for both the reservoirs are in the ratio of 2 is to 1. And the loading concentrations of the drugs are in the ratio of 1 is to 2. So reservoir 1 has two times the area where it can release the drug, but the concentration is 1. But reservoir 2 has only one times the area where it can release the drug, but the concentration is 2. So much higher concentration, less releasing area, much lower concentration, much lower concentration and more releasing area. So what is the ratio of mass of a drug released in the same amount of time for these two reservoirs? So if both of these reservoirs are studied for the drug release, uh, so for a given time, how much of drug is released by both of these reservoirs, and what is the ratio of this amount of drug that's released by both the reservoirs, right? And basically assume the reservoirs are flat and non-erodible, and the drug diffuses through a semi-permeable membrane. So, sure. Yeah, she might have covered it, but I think there are a couple of us who are doing it for people who are probably not able to join the class at any of the given times, right? So that's okay. Okay, so in that case, I'll skip this. I'll quickly go over it. So ratio of drug releasing areas is A1 is to A2, which is 2 is to 1, and the ratio of loading concentration C1 is to C2 is 1 is to 2. Yeah, so now the rate of drug release is proportional to both the drug concentration and the area of release. The mass of drug release is given by the equation. Basically, the amount of drug that's released is directly proportional to the concentration and the area, right? C1 times A1. So if we take the ratio, what would you get? C1 times A1 by C2 times A2. Now we know A1 is to A2 is 2 is to 1, and C1 is to C2 is 1 is to 2. So if you substitute these into the equation, because we are taking the ratio, we can directly substitute. So 1 by 2, 1 by 2 by 2 by 1, which is 2 by 2. The answer is 1. So uh, same amount of drug basically diffuses through both the reservoirs. So if you double the concentration and half the releasing area, or if you keep the concentration same and increase the releasing area in both the cases for a given amount of time t, same amount of drug is being released. That's the question. And the next question is consider a microsphere of diameter 1 micron. Calculate the number of such particles that would be present in a 1 mg given the density of the material is 1.3 grams per ml. Uh, do you guys have an idea how to solve this? So they're saying it's a microsphere of diameter 1 micron. So we know it's a sphere and we know the diameter, which means we know the radius. So we know the radius, which means we can calculate the volume of the sphere, right? So volume is 4 by 3 pi r cube. And you know the volume, you know the density. So what would that give you? That can you can calculate the mass of a particle, right? So for one particle, uh, you can calculate the mass of one particle. Now, can you calculate the number of such particles that would be present in 1 mg? So if you know one particle weighs this much, uh, so you would know then how many of these particles are there in 1 mg, because you know one particle has this mass. So if the total mass is this much, how many particles are there? Fairly simple, straightforward calculation, right? Yeah. So volume of sphere, you know, because you know the radius, and once you get the volume, yeah, you can convert the volume interchangeably. So one micrometer cube is equal to 1 into 10 power minus 12 ml. So once you convert that to ml, you also know the mass of one microsphere because you know the volume and the density is given. The reason you're converting here is because the density is in gram per ml. So now you know the mass of one microsphere. That would help you calculate the mass of or the amount of the number of microspheres present in any given mass. So it would come out to be 1.469 into 10 power 9 particles, which is also equal to 0.1469 into 10 power 10 particles. Okay. So the last question, I think, reservoir system refers to what? Is it a system saturated with drug surrounded by a degradable membrane? Uh, uh, is it all the systems with zero order release rate? or all the systems with first order release rate, or systems which have non-degradable membrane and are supersaturated with the drug, all systems with second order release rate, and systems with semi-permeable membrane which degrades with time. Or what is the reservoir system referring to? So whenever you think of a reservoir system, the first thing that should come into your mind is, so it's a reservoir, right? So if you look at dams and reservoirs, reservoir has a lot of water. So a reservoir system contains a lot of drugs. So it's super saturated with drugs. So that's the first thing that should hit your mind. So a reservoir system is always super saturated with drugs, and because it's super saturated with the drug, you don't want the membrane to be degradable, right? So if it's degradable suddenly, if it's degrading in your body, there is this release of very high amounts of drug. It might be toxic and kill the person. So you want whatever is holding this high amounts of drug to be non-biodegradable, so that it's as lasting as possible in the body, and the drug is slowly being released through some other way. There could be an orifice, so on and so forth, right? So that's that. Those are reservoir systems which have non-degradable membrane and are super saturated with the drug. Okay, so I think we are at the end of the session. Uh, so do you guys have any questions?
No, sir.
Okay, great. I think 3 o'clock, I'll do the week 3 session, so join if you have time. I'll see you guys then. Okay, bye.
Thank you,
Bye,
sir.
sir.
Bye.